Hello and welcome back everyone. This video will discuss about binary exponentiation, and before proceeding towards the topic, let us recap what is the meaning of exponentiation and its few of its property, which will be essential to understand the idea of binary exponentiation. Let us say anything of this form, a raised to b, where a is multiplied b times, is the idea of exponentiation. And here a is known as the base and b is known as the exponent. This is done b times. Now the process of exponentiation is cleared. Let us dive into few of the properties which will be essential to understand the idea of binary exponentiation. First property is a power 0 is 1 and anything raised to 1 will give us the same value. A raised to m whole raised to n is equal to saying a raised to m times n. Whatever idea has been discussed regarding exponentiation can be converted into a pseudocode, and this will be a brute force approach, and the name of the function was exponent multiplication, where base and exponent is passed as a parameter. And one thing that has to be kept in mind, that exponent has to be greater than or equal to 0, but if it is equal to 0, answer will be 1. If it is greater than 0, then only following execution will work out. Here result is the value initially having the value of 1, and then the loop is run to update the value of result like by the base, and at the end of the loop completion, result should be printed by the function. Let us try to figure out the time complexity for the method. This will take order of 1 time, and loop is executed for the exponent time, which in the worst case will be performed exponent time, and return function will be executed for order of 1 time. Hence time complexity will be big O of exponent, and in worst case scenario, exponent can be equal to n. Hence this can become an order of n solution. Is this the efficient solution? No. Why no? Because if either a or either base or exponent is very high value or very large number, this approach will become slower, as n minus 1 multiplication takes place in each iteration. Due to that, this approach will be slower. Is there any better way to solve this method? Yes. And that can be done by exploiting the property of a raised to m raised to n property, where here a times 2b or a power b square. If this is written this way, then exponentiation becomes faster. This is not possible in the naive-based approach. So if any exponent can be represented in this form, then this method will become faster. And this method is known as the binary exponentiation method, or exponentiation by squaring. Here you can see exponentiation is done by squaring, or square and multiply method. These are the names given to this approach. Our objective here is to calculate a raised to b, not a raised to 2b. So what one needs to do is, we need to divide b in such a way that this becomes in the form of 2b, and this is possible by taking b by 2 and a raised to b by 2. Only then it is of this form, which can be represented like a b by 2 square. So our objective is to make exponent of this form, and this is only possible if the exponent is even number. What would be the case if the exponent was odd number? Let's say this is the form. For that, what one needs to do is, we can represent like this for the odd number, and this can be calculated by taking help of this function. And so this is the idea of converting exponent into exponentiation by square method, and let us try to generalize this approach by writing the recursion function. Let's say recursion function is binary exponentiation of base raised to exponent, and this is only possible if exponent is greater than or equal to 0. For negative number, this approach is not applicable. If exponent is 0, answer will be 1. In case if exponent is even number, which will be like of this form, 2k form, then this can be represented like binary exponentiation base exponent by 2 square, similar to this form, a raised to b whole square. Similar to that form, this has been represented. And for odd case, this can be represented like base times binary exponentiation of base, and instead of exponent, because a power b 1 b, so this is left with a b minus 1. This has to be broken down into binary square form, so this can be represented like exponent minus 1 by 2 if exponent is of form 2k plus 1. and this will improve the performance of calculating the exponent as compared with the naive-Bayes approach. Why? Let us look through an example where, let's say, 5 raised to 10 has to be calculated. Using the naive-Bayes approach, here this will be done for here 9 times multiplication takes place. While using the binary exponentiation method, and also note here, every time it is being multiplied by 2 times, like base exponent by 2 times base exponent by 2. Hence, binary exponentiation. And here also we can see that it is being multiplied 2 times. One time with base and another time with binary exponentiation, base of base exponent minus 1 by 2. So this every time two times multiplication takes place, hence the term binary exponentiation. So 5 by 2 and 10 is an even number, so this can be represented like 5 raised to 5, 5 raised to 5. So here one multiplication will take place, and then 5 raised to 5 can be computed like 5 raised to 5 power 4. Here one multiplication will take place. Then 5 power 4 can be computed like 5 power 2 times 5 power 2. One multiplication. And 5 raised to 2 can be computed like 5 power times 5. One multiplication. And 5 can be computed like 5 times 5 raised to 0. This may be considered or may not be considered. So given that 4 multiplication takes place. The iterative approach for binary exponentiation method can be represented in the form like where b, which is the exponent, can be written in the terms of binary number, where ti is the weight attached to that value and it can take only 0 or 1 value, raised to 2 power I to get the number, and this is running from I equal to 0 to n minus 1. So taking this idea of exponent, just plugging at a power b, we get a raised to t of n minus 1 times 2 of n minus 1 multiplied by t a raised to t of n minus 2 times 2 raised to n minus 2 and so on till t0 to raised to 0, and this can be in short represented as the product of a raised to 2 power k, where tk is the value at which this will be set, like wherever the value of t I is 1, that value has been only taken into consideration, and this can be computed by repeated squaring method. The idea of using binary number is like in the recursive case, 2 times multiplication was taking of the same form. To get that idea, binary number has been used, okay? And this can be cleared by taking an example. Let us consider 4 raised to 25, where if 25 is to be written in binary form, this can be represented like 1 1 0 0 1. 16 plus 8 plus 1. And this can be represented by taking the weighted value 2 raised to power 4 plus 0 1 times 2 raised to 3 plus 0 times 2 raised to 2 plus 0 times 2 raised to 1 plus 1 times 2 raised to 0. This will give us the idea of which exponent has to be taken into consideration. This will give us the value 4 raised to 2 power 4 plus 2 power 3 plus 2 power 0. And here this can be simply written as exponent of product of k having the value of 0, 3 and 4 raised to 2 power k. And these are the values where tk is set to 1. And to understand the idea of how this can be broken down, another important property of exponent, which is a raised to b plus c, can be written as a raised to b times a raised to c, which simplifies to 4 raised to 2 power 4 times 4 raised to 2 power 3 times 4 raised to 2 power 0, which is nothing but the product of 4 raised to 2 power k. Tip code for binary exponentiation from like right side to left bit or from LSB to MSB is represented here, where function binary exponentiation right to left, taking a base and the exponent, and similar to the iterative method where one can have a look at this result equal to 1 and the loop has been executed, but here the loop will be executed only for the odd and even cases. So here one can check similar condition to naive Bayes approach, but here only odd case has been handled separately because that only needs to be handled, while the even case is just keep on dividing by 2, multiply the value and divide by 2. So this is for the even case and this is for the odd case. In that way, both odd and even cases are handled separately. So that is the idea of repetitive squaring. Here one can check. So this was to handle the even case and this was to handle odd case. And in the odd case, where in the recursive method it was shown like base into binary exponentiation of base comma exponentiation minus 1 by 2. So that has to be done. So this is being represented here in the recursive iterative form, while for the even case it was represented like binary exponentiation base x by 2. So by 2 we are dividing, so this was for the even case. Hence this will work for the LSB to MSB side and it will give us the result in log n. Binary exponentiation method from left side to right side, that is from LSB to MSB, can be represented like binary exponentiation left to right taking base and exponent value, and similar to the method right to left or iterative method, result is having the value of 1, and here the value has to be returned from n minus 1 to 0. For that reversal of bit, for that this has to be stored in an array, and once the value is been stored in an array, we can easily obtain the or update the result. So this is basically performing or adding itself. So it is like the result is updated by twice of itself. And once at any position when the value is 1 or set to 1, then that is being updated by the base. So that is adding 1 to the result, and this will work out, for the till the LSB is reached, and once that is reached, return the result, and this will be computed in order of log n times. 0 will have the value of 1. So let us say this will be executed from 4 to 0, and in the first case result is updated to 4, and then this will be exiting the third iteration. The result is getting updated to 16, but since the bit is set to 1, this is updated to 64, which is generally 4 raised to power 3. So these two bits has been updated. Now here basically it is 4 raised to 2 power 0 plus 1, and here it is basically 4 raised to 2 power 1 plus 1. Once this is done, the values are being updated, like result value is getting updated by 64 times 64, which is not 4 raised to 3 raised. So here it becomes 4 raised to 6, which has just double the value or square of the value has taken place, and here also square of the value has taken place. So resulting in 4 power of 12. Here square and addition can play, square and because it was an odd number, this was executed this way. So square will take 4 raised to 2 square times 4. So this is 4 raised to 24 times 4. So dry run on the even number, we get for I equal to 4, result is updated to 4 from 1, and for I equal to 3, first result will be updated to 16, and since the value is 1, this will be updated to 64, which is nothing but 4 power 3, and for remaining zeros only square operation will take place. So here 4 power 3 will become 4 power 6, because we are doing result into result. So this is just 4 power 3 into 4 power 3, which is 4 power 6, and again square operation will take place, which will result in 4 power 12, and again squaring will take place, which will result in 4 power 24. So that is how this will be executed. And it has been found that binary exponentiation from left to right is faster than binary exponentiation right to left.